In the previous module, we started out asking, does a reaction go? We decided that a better question was, is a reaction spontaneous? Our criterion was the free energy change, delta G. If delta G is negative, a process is spontaneous. But now that we know chemical processes can be reversible, what we're really interested in is this. Does the reaction go on to make mostly products? Ideally, we'd like our reactions to go 100% to make products, but that might not be achievable if the process is reversible. So how far does it go, and how can we tell? In order to think more about this, let's consider a ball on a ramp. The ramp is kind of like a half pipe with walls on either side, but the half pipe is not symmetrical. If we place a ball at the left-hand edge, we can ask which way will it roll? Of course, it'll roll downhill, so it spontaneously goes to the right. If we place the ball at the right-hand edge, it will go downhill, but it will not spontaneously go to the right. Instead, it will go to the left. Let's do this again, but now we'll move the location of the bottom of the ramp. Again, if we place the ball at the left edge, it will roll spontaneously downhill to the right. Whereas if we place it at the right edge, it will not spontaneously roll to the right, it will roll to the left. So we realize that the direction of spontaneous motion, left or right, depends on where we start. What is different about these two ramps is what happens if we start by placing the ball right in the middle. On the first ramp, the ball will go to the left. On the second ramp, the ball will go to the right. So it's fair to say that if we start in the middle, the direction of movement depends on the location of the minimum of the curve. Let's change our perspective a little bit and assume rather than a ball on a ramp, this is a plot of free energy, G, on the y-axis. And let's suppose the x-axis is the extent of the reaction. In other words, what if the left-hand wall represented the beginning of a reaction where there were no products and still 100% reactants? And the right-hand wall represented the theoretical end of a reaction where there were 100% products and no reactants left. The slope at any point in the curve would be the change in y over the change in x, which in this case would be delta G over, well, we don't have a symbol for the x-axis, so let's just think about this as delta G. Now, the sign of delta G, and therefore the spontaneity, is always thought in terms of the forward reaction. In the case of the ball on the ramp, it would be for the ball rolling to the right. In the first case, the slope at the 50-50 point is positive, meaning that rolling to the right is non-spontaneous. In the second ramp, the slope at the 50-50 point is negative, meaning that rolling to the right is, in this case, spontaneous. This corresponds to what we said earlier, that the direction of motion from the middle depends on the location of the minimum of the curve. The 50-50 point, 50% reactants and 50% products, is significant. Recall what we said about standard states. For solids and liquids, they just need to be present, but for gases, the standard state is the presence of a gas at 1 atmosphere pressure. The standard state of a solution is the presence of the compound at 1 mole per liter concentration. If both reactants and products are in their standard states with equal amounts of each, then the situation corresponds to the 50-50 point in our plots. We can then label that point on the plot as delta G0, where the superscript 0 indicates that both reactants and products are in their standard states. So, the sign of plain delta G gives us the spontaneity of a reaction, but it doesn't specify on the conditions. As we see with the ball on the ramp, the sign, and therefore the spontaneity, depends on where you start. Delta G0 also gives the spontaneity of a reaction, but starting in the middle with standard states. So it is delta G0 that tells us where a reaction will end up. Of course, if we let the ball on the ramp roll until it stops, it will end up at the bottom of the ramp in both pictures. In chemistry language, we would say that is where it reaches equilibrium. Notice that the slope of each curve at the bottom is 0. So a system reaches equilibrium or is at equilibrium when plane delta G is equal to 0. Be careful, there are two different zeros going on here. 0 as a value of delta G is different than 0 as a superscript. If we look at again where these two systems reach equilibrium and use the numbers on the x-axis, we would say that the first system is mostly reactants at equilibrium. This corresponds to a positive value of delta G 0. Starting in the middle, the system would prefer to go back to the left in the reverse direction. For the second system, mostly products are present at equilibrium. This corresponds to a negative value of delta G 0. Starting in the middle, the forward process is spontaneous and the system goes to the right. We'll distinguish between these two situations with a term called the extensiveness. The second situation, where mostly products are present at equilibrium, is what we will call extensive. When mostly reactants are present at equilibrium, we would say the system is not extensive. Extensiveness tells us where the reaction ends up. To summarize, the question we started off the previous module with was, does a reaction go? Not a very scientific question, not a great question. We then asked if a process is spontaneous. But now we realize that spontaneity, as measured by plane delta G, doesn't really tell us where a reaction will end up. So that's a better question, but still not ultimately what we want to know. We really want to know if a reaction is extensive. It gives a lot more information about a reversible process. That tells us if we get mostly products, and the criterion is the sign of delta G 0.